Hello, everybody. My name is Evgeny Mandrikov, and welcome to the session Dynamic Constants, Oxymoron, or Promising JVM Feature. I work at such a wonderful company as SonarSource. Maybe you heard about us. Maybe you use our products, Sonar, Sonar Cloud, SonarLint, etc. But today we are not going to talk about this company and those products. Nevertheless, I should put this huge disclaimer that whatever I'm going to say is just my opinion. And my employee can only dream to own this opinion. So, today we're going to talk about JVM feature, which appeared quite some time ago in Java 11, but it's not yet that widely used. As far as I know, the open source project on which I work at in my spare time, Java Code Coverage, was the first one to use this feature. And we find this feature quite useful, so today I'm going to show you why we find it quite useful, where it can be used, which problems we faced while we tried to use this feature, how we reported them, how they got fixed, etc., etc. Let me, by the way, check who is aware of Jacoco, who is using it. Oh, wonderful. Cool. So, while developing Jacoco, we tested on a quite range of JDK versions. As of today, if I'm not mistaken, it's 16.5. Why half? Because we also test early access builds of not yet released JDK versions, in order to find bugs there and report them so that they fix it before the release happens, so that you can benefit from this fix. It's quite funny process. Sometimes we find bugs in Jacoco, but I would say more often we do find bugs in JDK. We do report them and they get fixed. And here is a real disclaimer. I hope you had a great lunch. Did you? I hope you're not gonna fall asleep. My goal will be to show you a little bit of blood out of JVM. I will show you naked Java compiler. We are not going to use IDE today. We're going to use command line and call from the command line directly Java compiler. We're going to talk a strong language. Sorry for this. If you're not ready, maybe you can consider another session. We're going to talk deeply into the bytecode, not the Java source code. We're going to talk bytecode. And I will try to do within the next 40 minutes intense violence of your brain. If you're not ready, door is still open. If you all leave, maybe I could have a chance to visit another great session. So, are you ready? Let's start. So, a little recap. Maybe you know that Java nowadays has lambdas. When they disappeared, does anybody remember? Okay, to not amuse anyone, you both right. Java got lambdas as a language feature, as a syntactic feature in Java 8. But the internals of lambdas, what is under the hood of lambdas, invoke dynamic construction, it appeared already in Java 7. So don't worry. Little recap, what is behind lambdas. Here we have a simple example. We can call a run method. We pass to it runnable lambda. Inside of it, we do print hello Devoxx Poland. If we compile this and we call Java C, lambda example. If we compile this and decompile this using the standard JDK tool Java P, so call it, let's say, Java disassembler, with two important to me arguments, minus v verbose, minus p, private, protected, etc. I call them basically show me everything. Java p minus v minus p. And we're going to supply the resulting class file after compilation. We're going to see the bytecode. If we will look precisely into the bytecode, here is our example method. And in this example method, we do not see our string or system out println or whatever. We see invoke dynamic construction. Invoke dynamic construction is instruction introduced in Java 7 in order to provide support for lambdas and other dynamic features for other languages implemented on JVM, such as JavaScript, etc., etc. What is behind this invoke dynamic construction? the very first time JVM is going to encounter this instruction, it's going to call bootstrap method. This bootstrap method is going to construct a call site, basically object containing what actually should be executed. In case of lambdas, the bootstrap method is so-called lambda meta factory. Lambda meta factory constructs call site, which holds method handle, which is going to do the invocation, and lambda meta factory constructs special object representing the lambda from the body of another method that got compiled into your class file, which is not at all the same method as our example, which is another method. This method holds the actual body of the lambda. So this is a little recap of how lambda works under the hood. And at some moment in time, interesting question appeared. Can we use invoke dynamic, so-called IND, for constants? What if we want to hold some constant? Initially, this was not the design goal for lambdas for invoke dynamic. The initial goal was to design something where call site can be modifiable. At any moment in time, in fact, we can change the call site, we can mutate it and say, okay, instead of calling this method, now call that method. If we will try to use invoke dynamic for constants, we have a constant call site. Constant call site cannot be changed. It calls a single reference on a single method, and that's it. Unfortunately, while this works, it has quite some allocation overhead. We need to store this call site somewhere. Also, we have method handle under the hood in order to invoke the method, and indirection, invoking something through method handle, also has some overhead. This seems unnecessarily for constants. For constant, we can just need the value, why we need to call some methods, allocate some objects, etc. That's why I appeared idea of having so-called dynamic class file constant, also known as condi. Why it is dynamic? Because at runtime, its value is gonna be dynamically computed. Once computed, it's gonna behave like a constant, dynamic constant. What is good about condi? Condi resolves to a constant, to exact constant like any constant in your program, like number one, string, foobar, etc., etc. There is less overhead. Another nice property of condi is that JIT, usually, just-in-time compiler, does not trust even final fields. What does this mean? It means that for JIT, even if your field is final, JIT must assume that somebody, somehow, sometime could modify this value. You might ask how? Well, reflection. For condi, this is not the case. JIT can trust condi because condi is going to be stored as any other constant in so-called constant pool, and JIT can trust it. It enables various optimizations in just-in-time compiler, so again, we get greater performance. And another nice property of condi is if we have two invoke dynamic instructions in our class file, they have a different linkage stage. Every time, the first time each of them is encountered, we should call the bootstrap method, do the linkage with actual call site and the target, and that's it. But two condi instructions, if they have the same name, refer to the same constant, they do share linkage state. It means that we can use the same constant in various points of our program. Once the first constant is encountered, linkage happens, and there is again no overhead for other uses of the same constant. This is a nice properties of condi. How we can use them? For us, for Jacoco, it was pretty obvious how we can use them, so let's have a look into this. Let's say we have some original class. It could be as simple as a couple of instructions, but let's complicate it a little bit. Let's say that there is a couple of branches. There is one branch, another branch in else statement, and we want to record code coverage of this. We want to construct the execution flow in order to show you which branches were executed, which not. In order to do this, we can just record the fact that certain points in your program were reached. In particular, if we know that entry of your method was executed, then we know that method was executed. If we know that the last instruction of the if branch was reached, we know that true branch was taken. If we know that last instruction of else branch was reached, we know that false branch was executed. Simple as this. What is this prop? How we can record that certain point of your program was reached? Any ideas? We have some requirements on this recording. This recording should have minimal runtime overhead in order to not impact performance of your application. It should not have side effects on your application. It shouldn't throw exceptions, etc., etc. Preferably, it should not allocate some memory. Preferably, it shouldn't allocate anything on a stack. And it should be thread safe. We don't want to break thread safety of your application. So, any ideas? Okay, don't worry, it's not the hardest part, so wake up after the lunch. We're going to come to much more harder parts. I'm going to help you. Apparently, the easiest and the smallest way to record execution of certain point in your program is just a Boolean array. It has all the properties that are required. It is identifiable. Index in the array identifies the point in your program. It's thread safe. If you write true into the same index into the array, it doesn't matter how many threads write true there, because at the end, everybody would observe the true value here. There is no writes of false. So this is how we can record the point in the execution. But we also need to get this data back to save it on the disk in order to later to construct report. So this array should come from somewhere. It should come from instrumentation agent, which instrumentates your program to insert those props. So from where do we get it? Well, we need to call our runtime, our agent, and ask, hey, could you please give me props for the given class name? I would like array of the size, how many props I want, 3 in this case. And here is class identifier, which is just some checksum of the class. Why we need class identifier? Because the same JVM instance might contain multiple classes with the same name but different content, because they can be loaded by different class loaders. So here is how we obtain this array of props. Do you see problems with this approach? Static initializer, here we initialize static final field, we store the value here, we call some method to obtain array. Anybody? Okay, no worries, I'm gonna help you. Now you're gonna enjoy the hardcore part. In order to answer on the question whether the previous code had some errors, let's look at something simple, stupid, so that you would be able to answer on some questions. Given the following program, there is public static void main, there is some class, we construct this class and call method from this class. And in this method, we have assertion, whether 1 equal to true. Will we get assertion error? Yes or no? Right, it depends. If we start our application with enable assertions and we enable assertions for this class, you could also specify for which classes to enable assertions, then we're going to get assertion error because obviously 1 is not equal to 2. If we're going to disable assertions, we're not going to get assertion error. Simple. Let me complexify this a little bit. Now I have the same child class. It extends from some base class. In the base class, I have static initializer. Inside of a static initializer, I construct child and call some method. And in our main, I just construct child. So what's going to happen in this case? Do we expect assertion error or not? Or it depends? what changed? Why you are puzzled? It was so easy to answer on the previous question. I just added, what, 5 lines of code. Please wake up. Who thinks that if we enable assertions, we are gonna get assertion error? I do think. That's correct answer. What thinks if we are gonna disable assertions? Are we gonna get assertion error? Who thinks that no? This is a wrong answer. I think we're still gonna get assertion error. If you don't believe me, then please read Java language specification. Java language specification says an assert statement that is executed before its class or interface has completed its initialization, this assertion is always enabled. There is no way to disable this assertion. And we call some method at a time when child is not yet initialized, because in order to initialize child, we first need to initialize base, which calls this method. That's it. We're gonna get assertion error no matter what. Why Java language specification decided to do like this? It makes no sense, right? It's against any logic. Well, this is implementation detail of how assertions are implemented in the compiler. So if we are gonna look again into the bytecode, but we are not gonna do this, I'm gonna simplify the task. I'm gonna look into the bytecode and then provide you an equivalent Java code. Equivalent Java code looks like this. In order to store a fact whether assertions enabled or disabled for particular class, Java compiler generates a special field, $assertions disabled, and Java compiler initializes this field in static initializer by going into runtime asking, hey, could you please tell me whether assertions enabled or disabled for this class? In order to initialize child, we first have to initialize base, and child's static initializer is going to be executed only after this, only after initialization of base. So the static initializer is not executed, and what is default value for the Boolean in Java? False. So assertions disabled, false. So we're going to get assertion error. Implementation detail, it's ugly, but okay, what can we do? We can just put it in Java language specification. How this relates to our previous example of Jacoco? Well, it's the same code. It's exactly the same approach. We store the Boolean array in a new field. We initialize this Boolean array is in the static initializer. So we're going to get a null pointer exception because default value for array references is null. Here is the problem. How did we solve this problem? Well, let's do lazy initialization instead of using static. We're going to have another method which contains simply following logic. If we don't have data, let's initialize. Otherwise, we have data, let's just return it. Is there any problem with this? Wake up. Who thinks that there is no problems? I do. Who thinks that there is a problem? Well, I also do. Who all others? What do you think? Well, you're right. The answer is all others. You're right. The answer is, as quite often happens, it depends. This code was working perfectly fine before JDK 9. This is a valid code. It's okay to do like this. But after JDK 9 build 127, this is not okay to do like this. Because JVM, before OpenJDK 9, was never verifying Java virtual machine specification property, which says you cannot store in non-static initializer method, you cannot put the value into static final field. But that's exactly what we are doing here. This was working perfectly fine for many, many years. And then they decided to finally verify this property and to throw illegal access error. Because, well, yes, You cannot write such Java code which stores something into static final from non-static initializer. But it was possible from the bytecode. So what do we do? Let's just remove final. Easy solution, right? Anyway, JIT doesn't trust finals. Final makes no sense here. We can remove it, right? Or no? Well, yes, except we have interfaces. And in interfaces, everything is implicitly static final. We need a static initializer here. Why do we need to instrument interfaces? Before Java 8 and interfaces, it was impossible to have executable code. But unfortunately, starting from Java 8, starting from the same time when lambdas appeared, now you can have a default methods in interfaces. So we need to inject all the machinery in interface. What do we do here? Well, in order to answer on this question, we should understand whether with interfaces the same problem of initialization could happen or not. If it could not happen, it's okay to use static initializer and we are done. If it could happen, we again need a method, so we need some different solution. Let's have a look. We have such simple example. We need to construct similar case of a cycle of initialization when we will initialize child when basically base gonna call something on a child before child initialize it. Can we do this or not? Again, we should look into our Bible in Java language specification, which says when a class is initialized, its superclasses are initialized as well as any super interfaces that declare any default methods. Okay, let's add a default method into the base. Then we would like to observe the call of some method from the base in the child. So let's call this method like this. In this some method, why not just to observe that it can execute some code? Let's just throw assertion here. Let's don't bother with this checking assertions enabled or disabled or whatever. Let's just throw it. And let's observe initialization of child. So let's initialize some object here and also print something. So now we need to trigger initialization of child. Java language specification again helps us. In order to trigger initialization, we need to create an instance or call a static method. Okay, let's create an instance. Now we have this code. There is two possible outcomes. Either we would see assertion here, base, which would say that base method, base interface called the child method, or we will see first printed child and then exception base. In the first case, we have the same problem of cyclic initialization. In the second case, it's all okay and there is no such problem like we saw with classes. So which one of two outcomes you think is gonna happen? And let me help you. You know the answer. It depends. So we're gonna see base if we run on JDK version 8 update 40. We're gonna see child printed, exception base thrown, and a JVM crash. If we run on JDK above update 40, but before update 152. How we discovered this? We've been constructing independently with my colleague who maintains also Jacoco, with another colleague. We've been constructing exactly the same example, but we've been sitting in two different locations in the world, in two different countries and cities, and we've been using two different JDK versions. Imagine our surprise when one of us reproducibly gets crash, and the other one does not. Okay, what happened at... what's gonna happen if we are gonna remove throw statement? We are gonna see that base is executed, base calls a method before the child is initialized, and there won't be crash. So the reason for the crash is just the fact that we throw exception here. After update 152, we got another behavior, which is first we're going to see child printed, then base calls a method. And actually, this behavior is correct according to Java virtual machine specification. Whatever we've seen before was a bug, which we reported, which got fixed. But unfortunately, we got now a certain range of GDK versions where we still need to do something to avoid this cycle initialization and to not have null pointer exception. But we cannot use non-final field because in interfaces it's implicitly static final. So okay, let's use another pattern, not a lazy initialization, but just a slow pass for the time when field is not yet initialized and static initializer wasn't called. Yes, this incurs a little bit of performance overhead, but sooner or later, and very soon in fact, interface is going to be initialized, so this branch is going to be optimized by JIT compiler, it's okay. Bam. Why we're talking about all this? I hope you did not forget this. We're talking about all this because of constant dynamic. Constant dynamic is a such nice feature that allows us just to remove all this boilerplate code and replace it with a single constant. Instead of dealing with all these initialization troubles, we can just say, please load dynamic constant at a time when we need this props array. If we use this dynamic constant into methods, you remember the nice property, initialization will happen only once, exactly what we need, no runtime overhead, etc., etc. And it's exactly the same code, no matter what, class or interface. No need to have this special strategy, whether it's one or another. Nice. So we did this. This also has another nice property. Every time we need this props array, for the performance reason, we cannot ask it from the runtime, pretty much like assertions disabled or enabled, because going to the runtime and obtaining the array is costly operation, which involves synchronization, etc., etc. So we don't want to do it always. That's why we wanted to cache it locally. But to cache it locally before constant dynamic, we have to introduce field. This is not nice because all the tools which do reflection on your classes, like serialization frameworks, they're going to observe this field injected. This is not nice. Constant dynamic is not visible through reflection. So there is no problem. There is no more field. Serialization frameworks can sleep peacefully. Nice. Less overhead. We did this, we implemented, we tested, and immediately we encountered another JVM crash due to the fact that for some reason, while implementing this feature in JVM, nobody tested the case when type of a constant dynamic is array. They tested everything, integer, string, double, float, etc., but not an array. This was causing crash, assertion error, etc., etc. But okay, we reported it. Unfortunately, we found it 2 releases after constant dynamic appeared because it's spare time project for us. We don't have much time working on it. So there was some delay. But it was fixed. And it was backported. Unfortunately, again, because there is a range of GDK versions where the fix is not present, and maybe you are running this GDK version, I don't know, we need to do some workaround. And workaround was, okay, let's use object for the constant, but immediately let's cast it to the Boolean array. This works. After we did this, we encountered another crash. If our agent, if our recording of code coverage is improperly configured, for example, it cannot create a file on the disk or something like this, it's gonna throw exception. And this exception happens in the static initializer. As soon as we do this, and this happens on the path of initializing dynamic constant, JVM crashes. Again, We reported this, again found it a little bit late because we didn't test it incorrect configurations, but our users do. Thanks to them, we reported a bug to the JDK. It was fixed, and again, it got backported. So benefits for you. Workaround for us, well, as simple as don't throw exceptions. No, more seriously, instead of doing static initialization, we got rid of static initializer. We still throw exception, but that's okay as soon as it happens, not in the static initializer. Again, our users test much more than we do test. For example, they use another alternative JVM implementation, OpenG9. And they encountered another problem that it also crashes. There is a missing garbage collector barrier. We reported this there, and this also got fixed. Bam. So, where else we could use Condi? Is it just for Jacoco developed? Probably no. Probably there should be other use cases. One of the obvious use cases, we could finally fix this problem that is written in Java language specifications, that assert statement that is executed before class or interface initialization is always enabled. We can use just constant dynamic here, and this problem vanishes. Unfortunately, this was not yet done. I don't know why either, because it's a low priority for JVM JDK developers, or everybody got used to live with this, so it doesn't bother anybody, or because this actually involves process of changing Java language specification. I don't know. It's not yet fixed, but it's possible already. And here we can use Condi, and we don't even need to introduce any new bootstrap method, because JDK already comes with some handy bootstrap method for constants. They recite in Java lang invoke constant bootstraps. There is already a method, bootstrap method, which allows us to initialize such a field as assertions disabled. We can say, okay, constant bootstraps, in order to initialize this field, please call this method with these arguments. We can even code and try this without modifying JDK. We can use a wonderful bytecode manipulation library, so-called ISM, which Jacoco uses under the hood. And here is how to construct constant dynamic. Not that hard, actually, if you can read documentation. Where else we could use constant dynamic? Well, non-capturing lambdas. If we have two methods which declare exactly the same lambda, and they don't capture any variables, we can actually say, well, this is a constant. And again, we are going to get all the benefits of constant dynamic. It's going to be initialized once, so less overhead, because overhead currently of this code is to initialize exactly the same lambda 2 times. Probably we won't have much time, but I will try to speed up. Another question for you. This was my quiz in Twitter. Here is a link on it quite some time ago. If we declare enum, and inside of enum we declare some constant values, how much constant values in enum we can declare? Any ideas? And again, I bet you know the answer. Altogether, it depends. It depends on particular source code to bytecode strategy of transformation implemented by compiler. And different compilers do implement this differently. Why it depends on this strategy? Let's have a look. Let's compile this Java C, this example. Let's decompile it, Java P minus V minus P. You remember my favorite command. Let's look inside. What do we have here? Enum constants are actually fields in the class. And even famous smart people like Heinz answer on this question incorrectly. They do know that enum constants are fields. And they do remember that number of fields in a class is limited by Java virtual machine specification by 65,536. So the answer is this. This is as many fields as constant we would need, so this probably should be that value. Unfortunately, they miss the fact that all the values are also stored in another field. So at least -1. But you also could remember that the length of arrays is limited in Java virtual machine. It's much less than 65,000. What is the maximal size of array in JVM? I bet you know. It depends. It's about 32,000. Exact value varies by 1 or 2, again, depending on JVM implementation. So one could also say we need to store all those values in an array, so it should be around 32,000. But even this is wrong because people forget that, why we need this values field, because there is, on enums method values, which returns all the values of enumeration. What people usually forget is that there is static initializer, which has to initialize all the fields in this array. And in order to initialize all of them, we need to write some bytecode instruction. Quite a lot, actually, bytecode instructions, and there is another limit. This limit is on the size of the method. The size of the method cannot exceed 65, again, something, 1,000 bytes. So we're going to get, actually, in the current Java-C implementation, what we can initialize, if I'm not mistaken, we can have about 1,000 enumeration constants. You might wonder, why do I know this? Why I even came to answering this question? Again, you are smart people. Our users really smart. They do want such big amounts of enumeration constants. And we discovered this because, again, we inject one more field which breaks all the contracts of just the JVM. Well, back to Condi. Why Condi? Because in order to initialize those fields, we can actually use, again, Condi. We don't need those fields. We can store them as a constants. We can overcome the limit on the number of fields. In order to initialize array, we also don't need anything other than Condi. We can use Condi and initialize this array. Not sure we're going to have time for this, but let's try. Another example. You all know the switch on enum, and you probably know that now there is a switch expressions. Do you remember when they appeared? And sorry, answer is not, it depends. Okay, no matter when they appeared, preview was quite some time ago. Hopefully they got finalized sometime later. They're gonna evolve in Java 21, but that's not important. What is important is that we can now write such a beautiful code like this. If we enumerate all constants in the switch, we don't need to write default. Wonderful. Let's have a look what happens under the hood. If we compile this, well, now we know probably where switch expressions appeared. We need GDK release 14. If we're going to decompile it, we're going to look in it. Yes, Java 14. Here is a switch. It contains 3 cases. Surprise. Default is still there in the bytecode, but compiler generates it for you. That's wonderful. What also we could notice is that this switch happens on some strange value. We never wrote in our code any field whose name is $switchmap$e. What's that? Let's look at this class, which got generated. This class indeed contains some fields, some static initializer. To simplify understanding, I'm going to again convert the bytecode into the equivalent Java code. What happens is, under the hood, Java compiler, when compiling switch on enum, generates a helper class which holds how the ordinal value of enum maps to the switch case. Why this is needed? Well, because of the split compilation, about which you probably heard. In Java, you can compile classes separately. You can have enum version 1, compile your switch. Then you can modify your enum and, for example, flip the order of your constants. Would be strange if this flipping would break the switch, right? If it also will switch all the switches. So what happens in this switch map is special code which asks the current value of ordinal of enum constant and stores the mapping from the current runtime value to the mapping that compiler observed while compiling the switch. This is wonderful. So here is how our switch actually looks under the hood. Is there any problems with this? Well, you can even, not dynamically, you can even... yes, you could introduce, for example, one more constant and counter this switch, and you will get incompatible class change error, but this is not a problem, this is expected behavior. The actual problem with this is we need to complexify a little bit example, and we are running out of a time, and you still not woken up after the grad lunch, as far as I could see. And this code is quite heavy. We didn't edit 5 lines as before, we added much more. What will happen here? Well, okay, I will help you. Exception initializer error, null pointer exception. This even happens, yeah, okay, how it's gonna look. We're gonna see cause, null pointer exception at our line number 1. This cause belongs to exception initializer error, which is raised on line number 5. And the stack trace is also gonna contain at line number 11 in the method that is never called. This source code doesn't contain any single invocation of a method never called. Why so? Well, okay, before we answer why so, somebody somewhere, if you know Kotlin or you're one of those people, they do say if your program has no nullable classes, nullable objects, null pointer exception cannot happen. Here is the source code. There is absolutely no single instance of nullable object, yet null pointer exception happens in the Kotlin. It's exactly the same problem. Kotlin compiler implements the same translation strategy as Java compiler for translating switches on enums. So what's the problem with switches on enums? 2 switches written in the same source file are going to be compiled in not 2 different switch map classes, but into the single switch map class. So in order to initialize one enum, we are going to call its constructor. In its constructor, we have a switch. This switch uses the switch map. And in the switch map, we already need what we are just trying to initialize. We already need the value of the all constants of our enum, null pointer exception. We can solve this issue also using Conda. Another nice addition, we can introduce a new bootstrap method that initializes this mapping for the switch by enum, and compiler doesn't need to generate any additional class, no tricks, no null pointer exception. All of this is just going to happen at runtime. Again, I don't know why this is not yet implemented. There were some discussions about that, about the fact that this can be done, but it's not yet done. Maybe one day this will be done. What other applications of Conda? Well, I think that singleton factory is another good application of Conda. Can anybody tell me how to implement singleton factory pattern? Maybe like this? Well, this is not nice, it's not lazy. Maybe like this? Well, it's not that performant, right? Synchronize that section, etc., etc. So, sorry? Use enum. Yeah, good point. We're going to come to this. In fact, very good and proper and correct implementation is double-checked locking. But if you would Google for this, you would find enormous amount of examples which actually wrongly implement this pattern. So I don't remember this by heart. I easily do make mistakes in this. So it's not nice. It would be nice if we could simplify all this. Well, there is simpler pattern which I do like. It's initialization on demand holder. We need to introduce additional class, and we get all the properties. We get laziness and thread safety, etc., etc. And this is similar to how to do this with enums. Well, this time Kotlin is nice. It helps us. It has a nice syntax to do what we just did in Java with these 15 lines of code. We can write couple of lines in Kotlin and we will get everything, thread safety and laziness, blah, blah, blah. Why not to have this in Java? And the way to have this in Java is actually lazy static final fields. There is even draft for this, so maybe we can dream one day this will be implemented. Maybe it will look like this, lazy static final singleton, or maybe const, because eventually this is const, however, with some lazy semantics. Maybe, hopefully. So, there is even more coming each day. Java 11 got dynamic class file constants, Java 12 got JVM constants API, everything what can be constable. There is JEB, which is not yet resolved, not even draft, but already a JEB, which provides intrinsics for LDC and invoking dynamic instructions so that you would be able to construct them at runtime. You wouldn't need ISM library for this, and so on. So, what are the takeaways of this talk? Nowadays, new powerful Java and JVM features, such as constant dynamics, they arrive very, very quickly. Nowadays, we have a very rapid JVM release cycle. Every 6 months, we get a new JVM with the new features. Preview, non-preview, finalized, etc. This opens possibility for many other features. As we've seen, this just opened some doors in Jacoco, the same way in other libraries. And not only for Java and JVM, it actually helps other languages implemented on top of JVM, like Kotlin, I don't know, Groovy, Scala, JavaScript, etc. So you, as a users, please don't wait. Don't be afraid to try them out. If you have some pet project, why not playing with some new features there? Maybe you will find a bug. It's not that hard. You just try. If it doesn't work, you take your simple example, you take your stack trace, you go to bugjava.net, if I'm not mistaken, or bugs.opengdk.org, and you record your issue there. Or even you can go to the mailing list and write there saying, hey guys, I just tried this, look at what I found. Maybe I'm doing something wrong, or maybe you implemented it wrongly. The OpenJDK developers are very welcoming community. They're gonna help you, they're gonna find the solution. So please do this. Don't be afraid. Try this out. And that's it. Thank you for your attention.